In this paper, we propose GaussianCross, a cross-modal self-supervised 3D representation learning via Gaussian splatting. Current point cloud self-supervised learning methods mainly rely on contrastive learning paradigms, such as point contrast and group contrast. These approaches typically generate two different views from the same scene and consider point-wise discrimination as a pretext task. However, there are some unsolved challenges. For example, insufficient structural discrimination due to irregular point cloud geometry. They also suffer from model collapse due to inadequate diversity in view augmentation strategies, and face scalability issues and parametric sensitivity problems. Cross-modal 3D pre-training methods use differentiable rendering as a self-supervised signal by comparing arbitrary synthetic views with real images for 3D scenes. But existing works focus on photometric reconstruction while neglecting geometric and semantic relationships, and require additional computational cost for view alignment. These drawbacks hinder their scalability. Therefore, in this work, we propose GaussianCross, trying to solve the above-mentioned challenges for better 3D representation learning. Our method processes the input scene point cloud by a backbone to obtain voxel features. Then, the coordinate transformation is applied to construct scale-agnostic representations for generalizable scene description across varying scales. We call this technique cuboid normalized Gaussian initialization. By considering transformed coordinates as Gaussian anchors, we get other properties from corresponding decoders. To further improve computational efficiency, we introduce an opacity-driven pruning mechanism. Finally, we leverage a tri-attribute rasterization splatter to render multi-view images, depth, and feature maps, enabling the model to pursue the underlying appearance, geometric structure, and semantic information. The rendered images are supervised by ground truth color images by L1 loss. The splat depth maps are also supervised by L1 loss with invalid pixels. For semantic map rendering, a potential challenge lies in that the dimension of visual foundation models is usually large, making it time-consuming to render such high-dimensional feature maps. Therefore, we tend to render a low-dimensional map. To address the dimension disparity, we implement a lightweight upsample projection head to align them. This design strategically balances computational efficiency with semantic fidelity, enabling effective distillation of 2D priors into 3D representations without compromising rendering performance. We name this part tri-attribute adaptive distillation splatting. In this table, we show the full fine-tuning semantic segmentation results on 3 different benchmarks. GaussianCross attains the best performance across all datasets under the self-supervised pre-training setting. It also outperforms multi-dataset pre-training strategies, like MSC and PPT unsup. Although supervised pre-training baselines maintain marginal advantages on ScanNet, our method establishes a new state-of-the-art on ScanNet 200. Consistent performance gains are observed on S3DIS under both Area 5 and 6-fold cross-validation settings, confirming its robustness. We also conduct comprehensive experiments on parameter efficiency via linear probing and data efficiency by limited scenes and point annotations. These results demonstrate the superiority of our proposed GaussianCross. Additionally, it presents significant improvement over previous contrastive learning methods on the instance segmentation task. We present all the performance in the image at the bottom right. In the left figure, we visualize input point clouds, UMAP results of learned representations, and corresponding synthetic RGB images, depth maps, and semantic-aware feature maps. From the results, we can observe that the learned point cloud representations are well clustered by UMAP on ScanNet, indicating that our GaussianCross can effectively learn meaningful and expressive representations. To further validate the feature quality, we visualize the dense spatial matching results in the right figure by calculating the cosine similarity between the query point and others. Moreover, we visualize the zero-shot representation on S3DIS and ScanNet++. Please scan the QR code for more details. Thank you.